Hello, everyone. Thank you for joining today's webinar, The Value of Real-Time Imaging, Integrating Particle Size Analysis onto Fluid Beds, Twin Screw Granulators, and Roller Compactors. This is our first session following the recent announcement of HORIBA's exclusive distribution right here in America for the Icon 2 technology. My name is Julie Chen Nguyen, and I'll be facilitating today. And let me introduce you, our speaker. So it's my great pleasure today to introduce you, our opening speaker today, Darren McHugh. Darren is the Icon 2 product manager at Innopharma. He received his degree in mechanical engineering from Technological University, Dublin. As a product manager, he is responsible for setting the vision and strategy of products, and he is the voice of the customer and facilitates a talented group of players to help steer the product roadmap. When he's not working, Darren likes to read up on developments for cutting-edge technology, trying off the home renovations, and going on adventures with his dog. Our second speaker, Chris O'Callaghan, is the head of engineering. He has been with Innopharma for more than 8 years and has worked across sales, engineering, building out the application space for the original Icon technology, and developing the hardware for the second generation Icon 2. He and his team manage the custom engineering projects required to successfully interface PAT systems with new and existing product lines in a continuous and batch manufacturing spaces. Outside of work, Chris has a bit of an obsession with 3D printing and has personally developed a high-speed, high-temperature FDM 3D printer for temperature-stable mechanical components. Pretty impressive. So now I'm gonna turn the floor to you, Darren. Please go ahead and share your screen.
There we go. Hi everyone, welcome to this webinar. My name is Darren McHugh. First off, I want to say thank you to Julie for creating today, and also thank you to the HORIBA team for hosting this webinar, which is about real-time particle size imaging and the value of integrating this technology inline onto process equipment such as fluid beds, twin screw granulators, and roller compactors. Okay, so let's jump in. Just to give you an overview about what we're going to cover today. Quick intro into Innopharma, who we are, then we'll get into the nuances of our Icon 2 direct imaging system for inline particle size measurement, what it is and how it does it. Next, we'll cover the practical considerations for implementation. This section is what I like to think of as ways to reduce the learning curve. Here, I'll discuss the cans and can-nots of direct imaging systems. Next, I'll cover the various interfaces for process equipment, and I hope the takeaway from this will be the level of detail and consideration required for successful integration, that it's high, but there's also a support group of expert engineers and scientists here, experienced to help you with embedding particle size technology inline. The next section is to do with applications, and this will be taken by my colleague, Chris O'Callaghan. He will talk to you about the various installations and studies conducted with the Icon 2, specifically to do with twin screw granulation, milling, and fluid bed granulation. He'll then take a deeper dive looking at where the Icon 2 was used to predict dissolution rates on a fluid bed Worcester Coating process. So stay tuned for that. After that, I'll do a quick recap and we can get into some Q&A. Okay, so Innopharma, a little bit of a company background about who we are. We were founded back in 2009 by Dr. Ian Jones. He's seen the market need for inline process technology and a shortage of skills in the pharmaceutical manufacturing market. And just in over 10 years, he's grown that out into 3 divisions. So we're made up of Innopharma Education, who advanced the careers of thousands of people providing flexible part-time blended e-learning solutions, which is becoming more and more relevant present day, for the high-tech manufacturing, pharma, food, and medtech industries. We also have our Innopharma Technical Services division, who provide contract validation engineers and technical specialists, again, to the pharmaceutical industry. And then there's us, Innopharma Technology. We develop various systems to analyze and control pharmaceutical manufacturing processes. So we're also involved in various EU research and innovation programs, but we're actually committed to providing solutions for the high-tech future of manufacturing and Industry 4.0. This picture on the bottom left is of our offices in Dublin, Ireland. And on the right is where we celebrated our 10-year anniversary last year. My director would like to clarify that in this picture, we're putting our hands up out of joy and not because we're being held up. Okay, a little bit about our products then and what's on the market. So we've worked predominantly in the pharma market, providing PAT sensors, but also provide technology and consultancy for industries such as food, chemical, agricultural industries, and so on. Here we can see the products on the left being the Icon 2, which is what we're going to cover today. Next is the Multi-Eye 2. This is our 4-probe near-infrared spectrometer. It is consistent with the Innopharma ethos of being a non-product contact real-time device. And it's predominantly used for reading moisture content, but also has a wide range of capabilities, basically where spectra can be compared to a known reference, a real-time prediction can be built. Next is SmartX. This is our new cutting-edge platform, which is leading the way for us in Pharma 4.0. This vertically integrated system can not only trend and track third-party sensors and process equipment, but it can also control them. So, for example, if you have a PAT sensor for particle size, this can interact with this platform to tell the spray pump on a fluid bed to either slow down to decrease the rate of granulation or increase it. Okay, next slide is just hopefully give you a bit of an idea about the journey so far for Innopharma technology. We started off with our first generation Icon in 2009. We're 5 years into our second generation Icon 2. And you can see on the bottom right here, our SmartX platform, the seed of which was planted back in 2016, is starting to see the fruits now. Just to give you a little bit of a feel about our journey thus far as a company. So without further ado, let's get into the Icon 2, our particle size technology. I guess some of the importance around this would be what the Icon 2 can be used for. It's used for things like quality by design, design of experiments, to measure critical process parameter changes on process equipment, and giving you that data back as a critical quality attribute, basically particle size. So on the top left here is the Icon 2, or the tin can as I refer to it sometimes. And then on the bottom left is the benchtop setup. So the system is designed to be used inline, but we also have a benchtop offering with an automated sample presentation stage. On the right is a few examples of images taken from the Icon 2 system, from a granulation process and a coating process, and we'll discuss those a little later on about the colors and such. Okay, if we look at the technical specs for the system, its measurement range is between 50 to 5,500 microns, which is backed by a traceable size verification standard. The software is 21 CFR compliant, GAMP5. We're also IoT ready with things like OPC, open communication platforms, being enabled on our system, so you can read out data. We can go into the brochures for more information about that. Next, I'd like to show a little video of the hardware, just to give you an overview of how it works. Here we can see the Illumination Ring pulsing, which is made up of red, green, and blue LEDs. And then we can see the camera system in the middle, which is on a motor to focus in and out. All this is encased in a GMP design that is ATEX rated, so it's all sealed. We have our mounting point underneath our M5 by 4 bolt holes, so we can mount it onto the side of process equipment. All that is communicated through a single umbilical cord for Ethernet and serial communication. And then we have our product plate in the back showing the unique identifiers and all its ratings. Okay, I just have 2 more little videos. This is the system in a at-line setup. So you can see the Icon 2 is pointing down at a sample tray on top of our automated sample presentation stage. It's showing live images on the left in our software called iPass, and that's reading in real time. Here we'll just mount some material underneath the system and start a session real quick. So it might be quite subtle in the video, but we should be able to see the top stage rotating underneath the Icon system. And it'll do that to grab a unique image of the material underneath the Icon. So this is just the at-line or benchtop setup of our system. On the right is our connections box, which all the communications go through from the Icon to the laptop. So that was our benchtop setup. Next is a inline configuration for the Icon 2. Here we have it mounted on the side of a, I believe a GPCG2 granulation bowl. It's a portable device, so it's easily transferable from inline to at-line or from process equipment to process equipment. It's, again, non-product contact, so we're looking through a port window of the process here, and we can see the granulation happening on this long window in front of us. So it's constantly grabbing new images, updating the particle size information, and reporting that back to the software. This green umbilical cable, or the communications cable, can run up to 20 meters back to the communications hub here. So that allows it to be located outside the process area or in a control room. Okay, so I hope those videos give you a bit of an idea of what the software or what the hardware looks like and how that interacts. Next, let's get into a bit more about the operation of the system and how it captures images. So we have the Icon 2 here pointing, looking at some material. We have this little animation where some material flows by the camera and a red, green, and blue pulse of light from our LEDs illuminates it. And then we get an image here on the right. So you can actually see in each particle in this image that it's illuminated with red, green, and blue, and that's very important for our algorithm for edge detection. So it's a pulsing system really, where it keeps flashing a light and grabbing an image consistently. Okay, a little bit more about our image analysis. So some traditional methods of detecting particle size would be something like Ferret's diameter or Martin's diameter, where they're actually projected into an equivalent sphere. So if we look at this diagram on the left with the granule, we can see the blue circle, which is an equivalent sphere for trying to match to the irregular shaped granule. But if we look at the green dotted line, that's the best fit ellipse. And that's how the Icon 2 system does its particle matching. So if we look at the image in the middle with the sample image, sphericity, and then at the bottom where the Icon does an elliptical fit, it does the best fit ellipse on that particle. So we feel it gets a tighter match on the particle size. This little graphic here just animates how it does that for projecting the volume. So we get the best fit ellipse to the edges, and then we get the major and minor axes from that ellipse, get the average of them for our third dimension, and that's how we're able to get our volume measurement for the particles. And it does this to every single particle within its image area. And just to talk a little bit then about particle size and D values, if someone's not familiar with them, it's a common term in the, I guess, particle size industry. So particle size or even particle size distribution is quite complex, and it should be. If someone is using a single number to describe their particles, they're probably failing to grasp the weighted situation. So even using upper and lower tolerance limits is not something that will accurately depict the width of the particle size distribution. So this is where D values come in. For example, if we have a D value of D50, which is probably the most common value or go-to value for particle size to describe it, we're only looking at the maximum particle diameter below which 50% of the sample volume exists. So that's what someone means when they say D50. But if someone was to use the D10, we're looking at up to 10% of the volume of that particle. So a typical particle size distribution could have a number of D values, but typically D10, D50, and D90 would give you a good representation of the width of your distribution. So that can be useful, very useful inline. If you're measuring on a fluid bed and you see your D10 values are starting to go low, it can be a sign that you're generating a lot of fines. There's probably a lot of attrition in your process. Or equally, if you can see your D90 values are starting to spike, you might be over agglomerating or over wetting your process. So that's the value of looking at a full particle size distribution. Okay, next we're looking at some of the data from the Icon system. This is a screenshot of an inline process, a granulation process. We can see that over time, the granules grew. We can get a live readout of that, and then during the drying process, they leveled out. So we have live images being displayed on the left. We have our histogram on the bottom right, and it's quite all interactive. Also, we have some data that can be exported as well from the system. This PDF on the left is an example report that can be put out, as well as this file on the right, a CSV file showing the metadata that's recorded by the Icon system. And this can be useful for building out your own charts or tables, or if you'd like to export them to an external data historian, that's an option with these CSV files. Okay, so if we get a little further into the geometry of the illumination, how the hardware works in terms of illuminating particles, we're looking at a cross section here of the Icon 2. So you can see the little circles are our illumination ring, and they're pointing down here at a port window. And things to consider here for the port window are its aperture or the size of the window. Is it wide enough to let enough light in? The thickness of the flange depends on how close the icon can get to this window, along with other thicknesses such as the gasket and the thickness of the window. And the window plays an important factor as well, because light from the illumination going through a medium such as air or glass will, the refractive index of which will change the path of the light. So if we get into that a little more, we can see our illumination ring, which is made up of red, green, and blue LEDs, is angled here at 65 degrees. So we have an optimum plane of crossover of light that we're trying to achieve onto the particles. And what we take into consideration for that is what I just mentioned, such as the refractive index, which has been shown here on the graph on the right. So the path of light can change due to what it's passing through. So we have a couple of equations there for that, but I don't want us to get hung up on the maths. We've developed a calculator on the optimum position for the icon, depending on what it's trying to measure through. So we can actually input a couple of values and figure out the best position to mount the icon. So sometimes a question would be, what is the distance the icon can measure at? And I would usually respond with what is the parameters, what is the thickness of your glass, what is the thickness of your flange, etc., to find out that optimum position. Okay, next we're actually moving on to particle presentation, the cans and can knots for the Icon 2 system. So here we have the first presentation, which is very similar to what we just looked at with looking through a port window. So we can see this blue line in front of the Icon 2 before it hits the particles. That's us looking through a port window. And for this type of presentation, we're looking for something that's a quasi-static body, so material has to be free-flowing and changing in order for us to measure it accurately. As with any PAT system, you have to consider the constraints with this type of measurement. So for us, in looking through a port window, some things to consider would be smaller particles. Are they obscuring larger particles in that particular position? So we'd have to look for a representative place to put the icon on a piece of process equipment. And then is maybe new material able to clear away old material? And that's what the bottom graphic is really showing here, that free-flowing material will clear away old material. So that's one way of presenting material to the icon. Our second method is actually where we're looking at a chute or a backing plate that is passing the material by the icon system. We find this very advantageous for material that might be a bit wetter or stickier than some, such as maybe twin screw granulation. We've seen great success with this type of presentation because we're able to apply either like something like a free-flowing material to the backing, such as maybe Teflon, or we're able to actually heat it as well to keep the material moving to prevent fouling. And things to consider for this then as well, as we've learned, are degrees of freedom. So the material needs to keep moving, and also to be wary of particle bounce as well as it goes down the chute, so it's in the optimum plane for presentation. Moving a little further into integration solutions, and what we consider when we look at a piece of process equipment really is the presentation and the representation. And what we mean by that is the presentation, as we just covered, the two methods, is that optimum for the Icon 2 system? And then the representation, is it where we're measuring, is it representative of what's happening in the process? And we have a fluid bed graphic here on the right. And as you can see, material moves up the center of the fluid bed, moves to the outer walls of the expansion chamber, and then flows back down the outside walls. And we found with the fluid beds that mounting the Icon 2 low down in the fluid bed is optimum for presentation as well as representation, because you have consistent flow of material past the icon. If we were to mount the Icon 2 too high up in the expansion chamber, we would only be seeing the smaller volume particles that have enough energy to reach that part of the expansion chamber. So we would probably get a skewed representation. Here's a couple of examples of our fluid bed interfaces going from lab scale to manufacturing. On the far left, we have it mounted on a fluid bed, a glass GBCG2. Then we can go to pilot scale, and then on the right, we have it mounted on, I believe, a GBCG30, or maybe some of our glass colleagues correct me that, 30, yeah, 30. You can see it there in the image just toward the lower window with the green cable coming out of it. So basically it's one icon, one journey from lab scale up right to production. You can use the same unit along that journey. Here's a few more examples of interfaces used on either batch or continuous processes. Again, on the top left here, now we have the mod cost system where the icon's been used at the exit of the twin screw granulator or at the exit of the dryer. The top middle image is at the exit of a twin screw granulator, and that's a good example of where we're looking at a backing material, looking down on a chute, and that chute's been heated to keep the material free flowing. The top right is at the exit of a dryer, where the material is actually held up before it passes through an airlock valve, I believe. The bottom left is on a filling line. This was a sample rig as part of a filling line to check for moisture and particle size of products before they were bagged. The bottom middle is a milling application, and then actually the roller compaction application on the right is also a milling application, with a slightly different interface. Okay, I'm nearly about ready to finish up, but I did want to touch on the topic of fouling because it's a very common question, and what we call fouling control, which is the prevention of ingress of material onto a surface. And it's something we have to consider for a non-product contact inline instrument such as the Icon. So there's different ways that we negate the fouling issue, such as using surfaces that are very smooth or have low energy, such as like Teflon, if that's possible, backing plate with Teflon. You can also use anti-static materials such as anti-static plastic windows. I'll touch on that in a second. Or we could actually change the material from, let's say, a borosilicate glass to a sapphire, not for its optical clarity, but for its actually lower coefficient of friction. And then we can use something more mechanical, such as a purge valve. And that's what these images on the right are. So the little blue tube above the Icon 2 is an actual pneumatic line that can be used for an inert gas like nitrogen or air if wanted. And the bottom image is that being positioned right in front of the imaging area of the Icon 2, and it'll intermittently fire a burst of air to clear the window. And then this last slide I have is to do with some other ways we've overcome fouling, such as getting rid of dead areas or dead zones inside a process. So this image on the far left is showing the inside of a bowl with a shelf above and below the window. And that can act as a seed point or propagation point for fouling to begin. So we've had fabricators in the past blend in the windows so they're much more smoother, there's less dead zones or areas for material to be hung up, and the material can keep free flowing. Here on the right then we have the an anti-static window. So on the left we can see it's from a milling process and the static charge has clung all the material to the window. And then on the right we've used a plastic window with special anti-static materials inherent to it to negate that process. Okay folks, I think that's a quick run through of the technology and how it works. I'm sure you might have some questions. We'll get them at the end. I'll hand it back to Julie now before we go over to my colleague, Chris, who will talk you through a few applications.
Thank you so much, Darren. And I'm going to go ahead and pass it over to Chris.
Thank you, Julie, and to Darren as well. So hello all, my name is Chris O'Callaghan. For anyone that missed the intros at the beginning, I'm the head of engineering here at Innopharma Technology. But my previous mantle was as product manager for the Icon technologies. So while Darren is now our product manager for those, I did a lot of this research myself. So I suppose I'm still the SME to some degree on these applications, but also I'm just a different voice to listen to for a few minutes. So what I'm going to do is, there's a lot of depth to these applications, and it's very, very difficult to cover them in the course of 15 or 20 minutes. And we have a number of them. So the approach I'm taking is I'm going to do 3 single slide summaries of 3 different applications. And then I'm going to get into a bit of detail on a 4th one around Worcester processing. But please do keep in mind, while I'm racing through, there are application notes, there are detailed studies and publications on each of these things that I'll be touching on and on others. So if anything that I mention takes your interest or seems relevant to you throughout, please do send an email either to myself or Darren or to your HORIBA rep looking for more information, and we'll be more than happy to provide that. So the first of these applications that I'm going to talk about in a single slide summary format is twin screw wet granulation. And this is an application we did a few years ago in conjunction with Thermo Fisher Scientific, who we're actually currently working on another project with that's very exciting and aligned with our control technologies that I'm not allowed to tell you any more about. But there's just another thing to pique the interest. Anyway, twin screw granulation, for anyone that's not familiar with it, is a continuous wet granulation process. And you can see in the image on the bottom right, this is the Thermo Fisher piece of equipment. We add in solid powder feeding at this point, and then just here, this little tube is the liquid addition. So the screws inside the barrel mix the material together and discharge past the icon that we have set up here. It's a very prototype arrangement. That was the nature of the study, but we think we got some really interesting results. Now, Darren touched on it earlier, or I think did a pretty good job of describing it. This material is warm and wet, so the moment it touches anything, it sticks. That's awkward. So this little chute that you can just about see here is both heated and highly polished to reduce the propensity of the material to stick. And it does work. Still somewhat material dependent, but different temperature levels and different inserts help a huge amount in preventing adhesion of material. The study that we did with Thermo was a couple of DOEs, full DOEs. And the real advantage to doing inline measurement is speed. Running on a twin screw, a continuous process, we don't have to stop in between experiments, which means every 5 to 7 minutes, we can execute another experiment. That's a time saving by just changing process parameters and giving it 30 seconds to a minute to reach steady state. But possibly the bigger time saving is this second point here. No time required for sampling, which isn't too time consuming, drying, which is typically tray drying done overnight, very obviously, you're waiting a long time for your results. And then offline analysis, which could be sieve analysis. And any of us that have done that know that it does take a good, even if you're very quick, 10 to 15 minutes per sample tested. That's major time consumption. With the icon, a whole 21 experiment DOE can be done in just over 2 hours at this 5 to 7 minutes per experiment time point. The other thing that the inline measurement lets you accomplish is it gives you an appreciation for the time-aligned data. This graphic up here demonstrates the DV50 over time experiments, each one about 3 minutes in length. Now, the theory tells us keeping all the parameters other than throughput the same, if we increase the throughput from 2 to 3 kilograms, it will increase the amount of shear in the barrels and should increase the particle size we get at the outlet. But if we look at this data, let's say that we sampled around the 1.5 minute point, it would tell us that our 2 kilogram per hour throughput produces less particles than our 3 kilogram per hour throughput. Now we know based on the theory that this is wrong, but if we were going just based on samples, tray drying, and sieve analysis, we only have that single data point. But you and I, looking at this graph, can see a very clear trend in that 2 kilogram per hour data that it has not reached a steady state. There was an issue. I think, if I remember correctly, we'd slightly overdosed liquid into the barrels at the end of the previous experimental set point. So we can straight away disregard that result based, purely on the data visible by saying this clearly isn't valid. And we could even repeat that experiment within that DOE at that point with our real-time available data. So that's one super high-level overview. The next one is around milling. And it was done in conjunction with Servier in Orléans in France. The specific process was hot melt extrusion, pelletization, and milling on a Hosokawa Alpine 100. They did a DOE where they varied mesh size and RPM. And the aim was to determine set points that gave them in-spec material, but also that minimized the risk of out-of-spec material. And I'll show you that in the data in just a second. The icon was integrated at the milling outlet, and if you can see my mouse, that's just around here. The icon's not actually visible in that image. Unfortunately, we were limited in the photography that we could do during the study, but we remanufactured this part here to allow icon integration while still allowing NIR probe attachment, which was a requirement of the customer. Here in this chart, you can see the summary of each of the 11 experiments executed as part of the DOE, showing a DV10, DV50, and DV90 average for the experiment. Now that tells us where we end up. That tells us what average particle size we get when we run at that combination of RPM and mesh size. But what's more interesting is, again, when we look at the time series, the time aligned data. In the graphic on the chart on the right hand side, we see the data from experiment 4, 5, and 6. Okay, that maps to these 3 experiments near the middle. And when I said minimizing risk of out of spec material, the upper and lower red lines denote the upper and lower limits. And we are trying to ensure we're between those limits, but we're also trying to ensure that we're between those limits with a minimum risk of going outside them. So while all 3 of these lines do fall within the limits, we can very clearly see that experiment 6, the green line, runs a serious risk of deviating below the lower limit. Similarly, experiment 4 comes somewhat closer to the upper limit perhaps than we would like, where 5 stays reasonably well centered between the 2 with minimal deviation. So again, this time series, this real-time data gives us an additional insight into our process and into the stability of that process. The last of my single slide overviews is on fluid bed granulation, and this is based around a recent publication in pharmaceutical technology about our SmartX system, but the icon plays a really key part. You can see it here integrated on our GPCG2 in our applications lab here in Dublin. The icon is there. The multi-eye that Darren mentioned earlier is just to the right of it. And those are both feeding data into the SmartX system to assist with making control decisions. We call it Advanced Dynamic Process Control, or ADPC. Was used as part of this study to determine the endpoint of the spraying phase. Rather than spraying a fixed amount of liquid, we spray until we hit a predetermined particle size. In the chart, we can see part of the effect of this. This is the particle size that we end up with at the end of our process. The brown box is non-ADPC batches, traditional control, traditional recipe-driven control. Spray a fixed amount of liquid, see where you end up at the end. However, the blue box is using this advanced dynamic process control, where we terminate our spraying at a specific size rather than liquid amount. So we're rejecting a lot of environmental and raw material variabilities that can creep into the processes otherwise. And you can see a much, much tighter control of our endpoint DV50. Remember, we're not ending the process based on the icon data, so this isn't essentially comparing our control value to our result. We're ending the spray phase based on the icon data. We still go through drying, but we end up with much tighter endpoint results. We've done some work since then as well, looking at controlling the inlet air flow rate based on the particle size to really connect the granulation theory of determining your air flow rates as based on the minimum fluidizing air velocity and the maximum transport velocities allowable, and picking an optimum point between those two. Anyone who's not too familiar with fluid bed, don't worry too much about that one. But essentially, in theory, the amount of airflow should be linked to particle size. But in practice, because we don't measure particle size in fluid bed granulation processes too often in real time, that's not done, and it's done in a more recipe-driven way. We haven't published that yet, but it's looking really interesting, and we will be publishing it soon. So if that's something that interests you, please by all means get in touch, and I'm happy to share some provisional data and send on some more information once we get to a point of publication. Anyway, on to the slightly deeper dive application. It's going to be on Worcester, and this is based on a study done a couple of GLAT and ColorCon, where we examined essentially, could we A, measure particle size growth in Worcester Coating, which is a fluid bed coating process I'll talk about in a second, and B, could we link that to the actual dissolution performance of the product? A couple of publications, and it was presented at IFPAC in 2017. Oh, it's longer ago than I remembered. Okay, why do we do Worcester Coating, or why is this important? Well, a lot of it is driven in the pharmaceutical industry by the demand for modified release products. Depending on what you're trying to achieve, we may either be trying to protect an active pharmaceutical ingredient in a dose from the high acidity of the stomach, if that's something that's going to destroy it, or we may want to reduce the frequency at which patients need to take tablets or capsules. And we do this through controlled release, sustained release, delayed release. There are different terms that all have slightly different meanings. But broadly, the way it's done is we apply a functional coating to a tablet or a mini tablet or a capsule or a pellet rather, which is then encapsulated. And the thickness of that coating has a major impact on either how quickly it releases or at what point in the intestinal tract that will release. So controlling these coatings to, microns of thickness is very important. They are very commonly applied using Worcester coating, and I've borrowed a video from our friends in GLAT to explain this one, although I can see from your end it looks more like a slideshow. It happens in a fluid bed, but rather than fluid bed granulation, we have an additional central column in this fluid bed where the air flow rate is much higher. And that sets up this kind of fountain arrangement of particle movement. At the bottom of the column, there's a spray nozzle, and that sprays upward, and the particles pass through this spray zone on their journey. They then go up into the expansion chamber, and with the hang time that they get in this fountain, the particle is actually dry by the time it drops back down into the bed. Now, they go around multiple times, many times, to achieve a consistent coating. But this is not like granulation where we wet the material. We actually dry it as we spray it. So the material in the bed at any time is very low moisture content, and that's what stops these pellets sticking together. It's a really excellent and highly controllable process. But no matter how good the process equipment is, we know that there are always uncontrolled ambient or material related conditions. And currently, a lot of this control is really done through recipe driven approaches. We don't monitor the critical quality attributes like the particle size growth, the moisture content in the bowl, things like that. It's typically just I spray a certain amount at a certain airflow rate at a certain temperature, and I should end up with the right results. Now, results do tend to be a little variable based on these incoming raw materials. Often that's acceptable, but there's room for improvement. So our position is this. It's an additive process. We're spraying material onto the particles. This is directly related to the gain of the particle. So we should see, as the film thickness increases, we should see an increase in size if we measure in line. Hey, that sounds like a good application for the icon. I'm not going to recover this slide, Darren had it earlier, but just to touch back to the methods of presentation, we're looking at this kind of thing. The icon looks in through a window down in the packed down bed of the equipment, and we have a nice single plane presentation of particles inside the window. It's just perfect for measurement. It's really ideal. For anyone that's into Worcester coating, and for those of you thinking, who's into Worcester coating, you'd be amazed. you meet a lot of really invested people, and I can't lie, over the last couple of years, I have become one of them. But for anyone interested, these are the materials and process parameters used. We had chlorphenyramine malleate layered sugar spheres, which we coated, so they have an active already layered onto them, and we coated them with a combination of sure release and Opidry. These are two formulated coating materials supplied by Colorcom. The GLAT had a 7-inch expansion chamber extension in case anyone is looking at the air volumes and thinking that looks really high. It would be for the slightly smaller variant of the GPCG2, and we were using a 6-inch PAT compatible Worcester bowl. That's just like a standard bowl, but it's got additional windows that you can see in this image here. For the study, we ran 2 experiments called CPM SR1 and CPM SR2. I might just call them 1 and 2. And we coated these to 20% weight gain with this sure release Opidry combination, and we took samples at every 2.5%. The icon measures constantly throughout, but to do the offline testing that we had to do with CamSizer and the dissolution, we had to take these samples. We also took a sample after 30 and 60 minutes of curing. The first piece of data I'll show you, this is based on ICON data, and it's nothing groundbreaking here. This shouldn't be amazing to anybody, but where we measure the film thickness, and film thickness is based on the growth in diameter. If this is our starting particle on the right-hand side, and this is a particle onto which we've added a film, as we measure the diameter, we measure the film thickness twice. So we subtract the starting diameter of the material from the current diameter, and then we divide the remainder by 2 to get F, the film thickness. So where these grow by the end of the 20% weight gain, where these grow to a 35 micron film thickness, that equated to a total diameter growth of about 70 microns. But really all we can say about this chart is there's an observable, consistent upward trend. And we'd be worried if there wasn't. We're adding material in there. If we saw it getting smaller or not changing in size, you know, that wouldn't really stand up. Nothing groundbreaking there. Can we trust the ICON data? I certainly hope so, but what we did was we checked it against a well-recognized offline standard at CamSizer. I'm sure you've all heard of it. You're on a HORIBA webinar. You're bound to be familiar with the CamSizer. This is all of the sample points we took in those 2 experiments, plus another couple of experiments we did with a slightly different particle size range. And for each data point, we have the size that the ICON reported at that point in time that the sample was taken versus the particle size as measured by CamSizer on the x-axis for that sample. Now, we don't expect different particle size analysis methods to agree one-to-one. Anyone who's done sieve analysis versus CamSizer or sieve analysis versus laser diffraction, it's common to see some variances between the results reported across different methods. But what's absolutely key and essential is that they must correlate to one another. And as you can see there, based on the R-squared value at 0.9895, the correlation here between ICON measuring in real time and inline versus CamSizer is very, very strong. So these samples that we tested for dissolution performance, and for anyone that hasn't seen a dissolution chart before, each of these lines corresponds to a sample. 5%, 10%, 15%, and 20% weight gain. So more coating on each of these as they progress, and then 20% weight gain after 30 minutes and after 1 hour. And this is the dissolution data for the first experiment, CPM SR1, for anyone that was keeping tabs. Now, as you'd expect, the 5% functional coating, it's a very thin coating, dissolves extremely quickly. After 15 minutes, we've already released more than 70%. And by about the 1 hour mark, it's up above 95%, essentially total release. As we add more coating, that release slows down. This makes sense. Nothing groundbreaking here, but we can use this data along with the inline ICON data to form a very basic model of how film thickness measured in line correlates to dissolution performance, and then use that as a means of prediction inline in real time. And for, again, anyone not too familiar with dissolution, the x-axis is the time that the sample spends in the dissolution bath. 720 minutes here. I'm not going to embarrass myself by dividing it, but I think, no, I will embarrass myself. I think that's 12 hours. So that is how long this test takes, 12 hours. You can't do it in real time. So if we can come up with some sort of real-time predictor, that's pretty important, or that's pretty valuable. Here we see the 120-minute time points correlated against the dissolution for each of the samples at 120 minutes on the y-axis against the film thickness as measured for each of the samples by the y-axis. And we do a very simple to this, but the equation of this line allows us to form the basis of, again, a very simple predictor. But the point of this study was not to create the world's greatest dissolution predictor. It was just to show, could this be done? We did this for all the other time points as well, just not to blow your minds. This is just for 120 minutes, but it was done for every one of these boxes at 15, 30, 60, 240, and so forth. So what we did then was we tested CPM SR2, the second batch, after we predicted the expected dissolution results. And this chart really is the last piece of data that I'll show, and I think it's the most meaningful. So take a moment to make sure you wrap your heads around this one. The dashed lines are the prediction based on real-time icon measurement results linked to dissolution performance as determined from that very basic model that I showed on the previous slide. The solid lines are the true results of the dissolution testing, which takes 12 hours and, you know, in the real world with lab waiting times and so forth, could take anywhere between 2 days and a month to actually get started. Dashed lines are inline real-time available data, and the solid lines are the true result from the dissolution test. The 5%, the 10%, the 15% all overlay excellently, as do the cured samples at 30 and 60 minutes. There's a bit of a deviation on the 20% sample, but some of that could be down to the stability of these aqueous compounds when they haven't been cured. So that 20% sample sat on a shelf for a month before being dissolution tested, whereas the previous disso data for the first experiment that I showed here was tested within a couple of days of being sampled. So there may have been a little drift in the results because this 20%, as with the other ones, was an uncured sample. So the prediction here, available in real time based on the icon data, overlays, I think, extremely well and shows real potential for this dissolution prediction inline. So with that, I'll hand back to Darren just to do a very quick sum up, and then I think Julie will use the last couple of minutes available just to manage any Q&A that we might have.
That's great. Thank you, Chris. Yeah, I just want to do another review page here. So I want to say thank you all. So I hope some of the takeaways from today are who we are, what we do, what the icon is and what it does, and basically how you can integrate the icon inline and the considerations around that for your process equipment. Chris went in depth. I think it was very interesting, the real world use case of the icon 2 for being able to predict something like dissolution. And yeah, I think we'll go back to Julie. Thank you.
Well, thank you so much, Darren and Chris, for your excellent presentation. Okay, I have a question from our audience. What are the limits in terms of the sample heterogeneity?
Okay, so that's a very interesting question that from the look on Darren's face as well, I don't think we've got before. I guess there are ways that you could interpret that, and I do apologize if I've got this wrong, but I assume you're asking about, I suppose, the difference between smallest and largest particles in a sample. So it's insightful, and this is clearly somebody who's worked with optical measurement technologies before, because while our particle size measurement range goes from 50 to 5,500, it does become extremely challenging to get an accurate, fully representative measurement if we have anywhere near that wide a spread of particle sizes. There are some ways to do it in line. Let's say you have a material that spans all the way from 50 microns to 5,500 microns. In line with flowing materials, while extremely challenging, it is just possible. But for something like benchtop measurement, broadly speaking, 10 to 20 times the minimum size to maximum. So if your minimum particle size is 100 microns, the upper limit of the really viable testable range there will be between 1,000 and 2,000 microns. Because we start to see obscuring issues otherwise, the large particles hide the small particles and so forth. I can't be more specific than that because it's extremely dependent on material type as well. If you have beautifully flowable materials and you look at different presentation methods, the options can be really limitless within the range. If you have extremely cohesive problematic materials, they will be tighter than that again. But sample testing is something that we do regularly. It's part of kind of the assessment and sales process for most of our customers. and something really that we'd be happy to do a kind of a specific technical discussion on for any potential material applications.
Thank you. And you can certainly email your questions or to be more specific offline by emailing us at labinfo@horiba.com. Okay, we'll move on to the second question. Can we receive real-time image output when using Icon 2 in continuous mode?
Yeah, it's a good question. Yeah, so the way the system works is it grabs every image, it analyzes them, and by default, just to save room on hard drives, those images are dumped. But there is a setting when you set up your configurations for an image storage interval. So you can set that as low as 1 second, so it grabs every image that you're analyzing, but you run the risk of filling up your hard drive very quickly. Or you can actually expand it out, so you're only grabbing one image maybe every minute, and they're saved onto the either the IPC or the laptop as part of the database. But if you're communicating over something like OPC, Open Platform Communication, it's important to note that images are not part of that. You can basically export your particle size data, the numbers, but not the images over that platform.
So that is the product manager answer, because he doesn't want any headaches. But I can tell you as well that at least one of our customers has a means of obtaining images in real time from the system. It's not directly supported, but there is, I suppose, an external API for an intercept of these images as well. Darren's throwing his eyes up to heaven because you're not meant to do that. I wouldn't use it for GMP applications. Essentially also because what would you be using the images for when the system produces this particle size data for you? But there is a mechanism to do it. But again, very important to note, it's not something that OPC and these kind of industrial standard communication systems really support. This data size is too big for those types of comm standards.
Thank you, Chris and Darren. Okay, an application different from Worcester Coating. Which is the correlation from Icon 2 with the sieving process?
That is material dependent. We have a couple of other application notes dealing with correlations to different measurement systems for different material types. I believe we've done, I've been informed previously that I absolutely may not mention the brand name, but some people that make a laser diffraction system that I'm sure isn't as good as the one HORIBA have. We've done correlation to that, and we have done correlation to sieve. It's safe to say they're not 0.989 R squared, because we're not dealing with materials that are quite as repeatable in size and shape as with Worcester pellet coating. But they were, I don't recall them off the top of my head, but again, I'm very happy to answer. I'm very happy to provide the additional information via email, because me throwing a number out here doesn't really give an appreciation the context of that data anyway. So by all means, drop an email to myself or Darren, and we'll provide you with the relevant papers that do other measurement method comparisons for other materials.
Thank you. Are there any validated sensors in FDA approved installations?
Yes. Yes,
Great.
yes, there is, but I can't obviously divulge that. But yes, we do have sensors in manufacturing plants measuring product at the moment as a, I guess, add-on method for just gathering additional data about their processes, but not technically part of filing just yet. But the idea being to learn more about their process and see if there's ways they can optimize it.
Thank you very much. Okay, here's one. Can you briefly describe a fertilizer application and your success?
Do we have a publication on a fertilizer application, Darren, that you can think of?
I can't think of the publication, but I can think of one application where we did with coated tomato seeds. That was like for
integrated fertilizer on tomato seeds.
Yeah.
We have done work with fertilizers. We don't, as far as I know, have a published application. Color is obviously a big variable with fertilizers, and with direct imaging, you can't work with very, very dark colored materials. So some will be more applicable than others. Just from my own experience, you know, fertilizers can range anywhere from white to light browns to kind of medium dark browns, all the way to black, depending on the content. Certainly black is off the cards for a direct imaging system. But we did do some work years ago on a coated fertilizer project, which were kind of light to medium brown pellets. That was successful, but didn't progress. It was related to a university. So depending on content, depending on material, very viable, or if very dark in color, not viable. Again, happy to work on an application and on material testing there. And I might be able to dig up some data on that previous work, but it was several years ago at this stage, and did not lead to anything that we had clearance to publish.
Thank you. And if you have any questions and would like to have a quote or take actions further, please go ahead and email us at labinfo@horiba.com. Anything else that you would like to add, Chris and Darren, before we end this webinar?
No, I just want to say thank you again. You know, we're looking forward to our new distribution agreement and working with you closer.
Absolutely, we are too. So thank you, everyone. For now, have a great day, stay safe, and we will see you at one or more of our future webinars. Thank you, everybody.
Thank you.
Bye, Chris.
Thank you very much.
Bye, Darren. Bye.